I'd like to introduce you to some ideas associated with linear prediction and also looking ahead towards the cross-synthesis application. Well, here's the concept. Imagine a real physical system which emits an output signal y of n. It's kind of a representative signal. Oftentimes y of n is stochastic or random in nature, but it can also have structure like a musical signal or all sorts of things. The notion of linear prediction applied to this system revolves around two key parts. The first being a time-varying digital filter, and it has transfer function h of z that's indexed by some block number k. There's an excitation function x of n, and it produces an output we call y of n. The general idea now is to find a set of filter coefficients and excitation function that will minimize the error between the actual y of n and the predicted y of n. Probably the first primary application of linear prediction was in linear predictive coding. This is a speech compression technique in which you simply transmit only the filter coefficients. Again, these are blocks of filters in time. You then transmit the excitation sequence, x of n, and these two are considerably smaller than simply transmitting the original y of n. That's how it ends up being compression. You can get extreme compression by skipping the x of n sequence altogether and simply transmitting the filter coefficients. You then drive the filter with some sort of fixed frequency excitation, and this gives the characteristic sound of what's called a vocoder. Sounds very mechanical, but it does produce recognizable speech. Vocoder, by the way, is an abbreviation for voice coder. Now, in music synthesis, we can apply linear prediction to the idea of cross-synthesis. We will derive the filter coefficients from a musical instrument, and then you could apply voice or speech or some other signal as the input. You could also go the other direction. You could make the filter match a voice and then drive it by an instrument. Now let me consider a single block that is a small fragment of our signal y of n, and the difference equation for the filter looks like the following. We have a set of a coefficients which multiply previous outputs of the filter. We then have a different set of coefficients, b, which multiply the previous inputs to the filter. So that's our x of n minus j. We can also work with the present input, so I'll change that to a 0. So again, we have our past outputs. We have the present and past inputs. Well, here's a new interpretation for the difference equation. We will think of y of n as being the predicted value given the past predicted outputs. And by the way, we can have a different number of past inputs, so let me change that to an m. Now specifically, we're going to use the so-called all-pole model. A coefficients are associated with the denominator of the transfer function version of the difference equation. That's why the A's are associated with all pole. Reason for this has to do with the original system that we're trying to model. There is no x of n to work with. Therefore, we will make our predictions of the present output based on past outputs only. Next, define the estimator of the output. I'll call that y hat of n, and the estimator will be, again, based on all of our past outputs, and we combine those with our coefficients a sub j. The prediction error then is the difference between the actual output sample from our original system, y of n, and we subtract our estimate y hat. Alternatively, we could express this as y of n is the estimator plus the prediction error. Now we already have an expression for the estimator. Now notice that this equation looks exactly like what we had before, the only difference being, well, again, just to emphasize the point, these expressions are identical. So apparently this error sequence corresponds to our term up here. Now earlier I had said that we were going to set m equals 0 for the so-called all-pole model, and this suggests then that this residual error can be thought of as the filter input x of n, or at least a scaled version of that. This residual error is not predictable, and it serves, as I say, ultimately as our filter excitation function. So returning to our linear prediction model, we think of it as our digital filter, which is based on the A coefficients only, driven by this prediction error sequence. And that produces the original signal. This is also, I guess, a nice model for the actual speech production process. If you think of it, the larynx produces the excitation, the vocal tract produces the filter, and that's kind of how that applies back to this idea of speech compression. Now, in order to choose the filter order, realize that the accuracy certainly goes up as n increases, but so does the actual computational cost of calculating all of those A coefficients. Reasonable values for music synthesis applications probably lie in the range of about 10 to 20. Another rule of thumb that some people like to use would be the sampling frequency in kilohertz plus 4. For example, if our system sampling frequency was 10 kilohertz, that would lead us to choose n equals 14. Another issue revolves around the choice of the frame size, that is, how much audio should we process at once. We need to try to match that range to whatever we think is a somewhat stationary version of the signal. And for speech, that's usually around 30 milliseconds or so.